Thank you, Professor. Thank you very much. It's a pleasure and I'm glad to be here today to give this talk. In this talk, I'm going to discuss the stability analysis, but from point of view of computational fluid dynamics. I'm going to start with some introduction about the instabilities, and later I will talk about one particular flow, which is the helical vortex. I'm going to describe how we solve the Navier-Stokes equations to generate helical vortices, and how we deal with the stability of this type of vortex. The second part of the talk, it will be like more like overview or general overview about stability analysis in the case of non-model analysis, and in the case of general stability analysis, like non-linear full non-linear stability analysis. So the first part will be application, and the second part will be overview about how we deal. I have to remove it. Okay, the question is why we study the stability. So the instabilities are everywhere in our life, in real application, real life, in industry, everywhere. So this is some of things instabilities is the Kelvin thermal instability. It occurs when we have shear flow with two different velocity. So there is the combination between the interface between the two flows, which creates a wave between the two flows at the same flow, but exactly at the difference of the velocity, and they create this type of vortices. The second type of instability is the Rayleigh-Bernard. So it's a thermal driven instability. Generally, for the thermal certification, generally we have the cold flow from down and the hot from top.
Could you get the sound of your computer, please?
You just turn off the volume.
Okay, done. So this instability happens when we have heating from down and the cold flow from up. So the hot particles going up, creating this natural circulation inside the flow. This is the thermal driven instability. Third one is the buoyancy driven instability. Here we have the lighter of the flow with the lighter density from the bottom and the heavier from the top. So the heavier fluid goes down inside the light fluid, and creating a mixing layer inside the flow, and it is unconditionally unstable. So the smallest perturbation will lead to the instability of this flow. Another one is what we call the capillarity-driven instability, when we have a jet of liquid and under certain conditions. So the jet will be divided in small droplets, and this is a competition between its minimum. The liquid need to minimize its kinetic energy, and at the same time the surface tension effect. So for this, it will be created like droplets, smaller and smaller. So why we are studying the instabilities in general? So we study the instabilities first of all to understand what happens exactly, how we go from laminar flow, smooth, to chaotic or to turbulent flow. In many applications, like here in the aerodynamic applications, so we need to know what happens exactly around the airfoil to optimize the shape or to control the flow. So we need really to understand what's going on. What is the first seed of turbulence, to understand and to design control strategies in passive or active way for the transition from laminar to turbulent. Sometimes we need to delay this transition as maximum as we can. As I said in the case of aerodynamic application, we need to delay this transition because turbulent derive drag forces. But in other application, we need to trigger this turbulence as soon as possible. Like in the mixing problem, when we have mixing process, we need this turbulence because it enhances the efficiency. Or when we have like the heat transfer problems, So the turbulent flow is benefic for the heat transfer process when we have cooling or heating. So as much as we have turbulent flow is better for the process. Another application when we can found instabilities is this type of vortex, and I'm going to talk about this one. So we have behind wind turbines or behind rotors in general, we have this type of flow which established, and he had this helical shape.
There's a feedback on that one. Good.
So we need to study the stability of this flow in order to minimize the distance between the turbines. Analysis about this vortex.
Can you mute your mic?
Speaker. Even numerical, but they have been ambitious. They are ambitious. So starting with the Wignall work, she distinguished three different of instabilities. And for one filament or one helical vortex, later on it was generated for a system of vortex. Anyway, so the most important part from this interest review is like from analytical point of view and numerical. When we consider the ambient flow, this type of helical vortex is always unstable, which is in somehow in contradictory with some experimental work where we can generate a stable helical vortex. So in here in 2011 and 2012, so these two teams succeeded to generate a stable vortex, and later on they studied the stability of this vortex.
So this is generated in the lab. Do you have an idea about how they generated?
They design the blade. Generally, the wind turbine, there is two types of design process. So in the case, they do like induced design. So they said we wanted to get this helical vortex, and they do the feedback how we can get the blade or the shape of the blade to get this helical vortex. But even I think we can see it even like in the proper behind the submarines. When we consider cavities, you can see there is some videos when we have exactly helical vortex for a long time when studying the helical vortex before it's breakdown. So to understand this contradiction between the analytical and numerical simulation for the ambient case and the experimental, so the objective of our work is to develop a numerical tool, so a code, including all parameters, so including Navier-Stokes equation with the viscosity and also with the existence of the blade inside the vortex.
So for you, the paradox is the fact that these are things that we can see experimentally.
They can be stable.
But yeah, so they should be stable, but the analysis shows that there is an analysis that shows that they are unstable.
Yeah, there is analysis and even numerical, but numerical considering ambient cases. Okay. And also, for example, in experiment, so the weight or the helical voltage generated is a solution or it's natural. But in the analytical solution, so they put the shape and the size to the component. So it's either it's not solution for the Navier-Stokes equations.
Also, the numerical solutions are unstable.
Analytical and numerical solution, but in certain conditions. So they considered no diffusion of the vortex flow, no displacement. So there is a lot of assumptions which are not really in experimental lab or when we consider the 3D Navier-Stokes equations.
So numerically, you're considering 3D oil without the viscosity. So you drop the viscosity. Or you take a reduced model. You take a reduced model, or you take the full Navier-Stokes without the viscosity.
The other people of the previous studies have done just the Euler, so without viscosity.
Without viscosity.
In our work, we are going to do the fully 3D Navier-Stokes equations with viscosity and everything.
So the paradox comes from the fact that they remove the viscosity.
They remove the viscosity.
It's not from because of the numerical error that they're doing.
No.
It's not.
Or the fact that they are interested in some type of perturbation that they in ways it's unstable. So, for example, they impose some type of vorticity inside the vortex. So inside the vortex is we have velocity and we have vorticity. So it depends on the type of the vorticity you are putting. In our work, we don't put anything. It will be the solution of the Navier-Stokes equation. We are just going to rotate the blade, and we see what is the solution of that generation.
Okay.
Okay, here just here, so the numerical tool, as I said, there is no exact solution for this particle helical motion. So we need to develop a solver for that. The solver needs to take care about the different scales for turbulence. For example, here we have the atmosphere, the boundary layer of the airfoil, which is very small scale in time and in space. But also we are interested in the wake, which is large comparing to the boundary layer. So we have very large spectrum of scales in time and in space. Just to have an idea of how much it costs if we did all of this. So if we take the smallest scale that we need to simulate and the largest one. So according to the Kolmogorov turbulence study, so we need Reynolds power 3/4. This is the range if we wanted to cut everything, all scales. So the ratio between the largest case and the small case is about Reynolds number power 3/4. Numerically, if we wanted to simulate that, so we need that Reynolds number power 3 grid mesh. So in our application, Reynolds number, it will be around 10 power 6 or 10 power 7. So we need always 10 power 15 grid mesh to simulate the full scale from the smallest one to the largest one. To my knowledge, there is no facility or there is no computational facilities able to do that.
But can you not like zoom, take a mesh that has a lot of points close to the where you have the small scales, and when you have the large scales, you take the mesh that is large to save some.
Yeah. The problem that you are generating the mesh, so you need to do adaptive mesh.
Adaptive mesh. Yeah, this one.
But even that adaptive mesh, you are gonna to gain in terms of grade or computational storage, but you're gonna to lose about the adaptation itself. So you need more iteration. And also using the adaptive mesh, you are losing also the interpolation. So when you move from one step to another, you need to interpolate again. So there is some errors coming from that. But anyways, it's costly. It's costly. So the idea is really to look for simpler model. So we can use turbulence model to gain some cost from the Navier-Stokes equation, or we can model the rotor. So there is some techniques when the rotor is not put as a solid, but is put as equivalent body forces. So like that, we can avoid really to study the full boundary layer of the around the blade and the detachment of the boundary layer. We are going to see just the effect of that on the flow without really the fluid structure interaction problem. And that's what we have adopted. This method is called the actuator line method. So it's based on modeling the rotor and solving the Navier-Stokes equation. So our work was developing this method. So developing the code, the Navier-Stokes equations, and the solver. Use it to characterize the helical vortex, and later on to study the stability of this helical vortex. So this method, as I said, is based on introducing the blade by its equivalent body forces. So it will be like source term of the Navier-Stokes equations. If the Navier-Stokes equation is a 3D without modeling, and we are talking about direct numerical simulations, we are solving all scales there. So it will be like predicted corrector. So at every time we calculate the forces from the blade acting on the fluid, and we correct the Navier-Stokes equations and go back for to calculate the aerodynamic forces. So the aerodynamic solver, it's like locally 2D. So we look for the aerodynamic approach for every section of the blade. The method we developed is second order in space by difference scheme. We use a staggered method to avoid the oscillation in the pressure. We use a variable change around the axis. We are in cylindrical coordinate, so mathematically we have some similarities around the axis. We have 1 over r, 1 over r squared come from the derivation. So we use a variable change to overcome this limitation of the cylindrical coordinates. We use a third order Ron quota for the conductive terms and the Crank-Nicholson schemes of the viscous terms. For the coupling problem of velocity and the pressure, we use the fractional step method using the Hodge decomposition. And in 3 steps. So the first step, we are solving the Navier-Stokes equation without verifying the divergence-free condition. We get pressure, or we get the velocity field with divergence is not, its divergence is not 0. We calculate the pressure, and we correct by this pressure again the velocity.
It's implicit finite difference, huh? Right.
Yeah, implicit and semi-implicit. There is sometimes are implicit, there is semi-implicit. So in general, it's semi-implicit, not really implicit. For the pressure Poisson equation, so to inverse the Laplacian, so we did it in a fast way. So we have we did Fourier transform along theta direction. So we get n theta or theta mode and dependent 2D cases in R and Z, which are 2D Helmholtz problem, easy to solve. And we go back later to the space domain using inverse Fourier transform. So in general, the order of the problem is fast and operations is second order in time and space. To validate this method, when we develop a code, so we need to verify and validate. So for the validation, we use the comparison with linear stability analysis. So there is Bachelor profile. Bachelor profile is swirling vortex. It's characterized by axial velocity and rotating velocity. This is a solution with the Navier-Stokes equation, and we have some study about the stability analysis of that one. So I take as initial condition this vortex, and I perturb it, and I see what's happened. To validate, so I have to get, for example, here I'm using this frequency, and I'm exciting the fourth mode in the azimuthal direction. So to validate, so I have to recover the same thing at the same growth rate as the linear stability analysis. Here for the linear stability analysis, how we measure this growth rate. So I'm using the energy in a section on my cylindrical domain. I calculate the Bradley energy, and the growth rate will be the slope of the linear variation of this energy. So here I'm presenting the time evolution of the vorticity. This is the perturbed flow. As you can see, there is a transient growth at the beginning, and there is a linear distribution, and later on there is the nonlinear effect. And the nonlinear term become like dominant, and we have the saturation, but the vortex break down, as in it's unstable, so it break down to form smaller scales.
So again, here the color represent what? The red and the blue.
It's positive and minus vorticities.
The positive and minus
positive.
But this is for which? For the test, like for
the
for
the test. In general, the bachelor vortex is like that. This is the R. For the axial velocity, we have this profile, Gaussian profile. And for the theta, we have this profile. This is the theta. So as initial condition, I put this in my domain, cylindrical domain, and later on I perturb this velocity. I perturb it, and I see what's going on. As I said, so we have 3 different regimes. The first one is the transient. So when the small perturbation grow, later on we have a linear regime. And because we are in non-linear Navier-Stokes, so the non-linear term become dominant, and we got what we call the saturation, non-linear saturation. So in non-linear, like the energy cannot go for infinity. So at some time we have to saturate. And I calculate the growth rate over this line, and I found a good agreement. Okay, so I got a good agreement between the theoretical and the DNS, the clinical simulation. So just to keep in mind, I'm using around 20 million grid for the simulation. That takes like 1 week, and I wrote it in parallel to accelerate the computation. It took 1 day, 2 days with this number of grids.
That's the fourth one, right?
Yeah, for one. So we developed it from scratch, but using some library for the FFT and so on. But we wrote the code from scratch. So once validated, so we use this code to generate a vortex. So here just I'm putting the blade, I'm rotating the blade, and I see what happens when I have one blade or two blades. And as you can see, we can get this vortex, well-established vortex stable as an experiment. So even we have, we did a comparison with the experimental lab, we have experimental data, and we got a good agreement in terms of the circulation around the blade, because we are using the same design of the blade. So once it's generated, so now I'm going to interest in the properties of this vortex. So the properties in terms of the weight, mainly the core of the vortex itself. So we did a zoom and we studied the vortex type inside. So in terms of the size of the ellipticity and also in terms of vorticity and velocity inside. That's the difference between the other studies. The other studies, they put like Gaussian vortex for their analysis without knowing if it's solution or not solution. In our case, we have the solution of the Navier-Stokes equation, and we are going to study what's the type of this vortex inside. Mainly the two parameters of this study are the Reynolds number and the tip speed ratio, which is like the ratio between the angular velocity and the axial or the mean flow. We use the different momentum of vorticity, the circulation, and the other environment to calculate the angular ellipticity, the core size, and the ellipticity of the core solution of the Navier-Stokes. Okay, here I'm plotting the vorticity inside the vortex for different time, but for a given theta. So I'm fixing in theta, and I follow the vortex in time, and I plotted this vorticity behavior. Later on, we try to find some scales. So for the vorticity, I took the maximum of the vorticity as vorticity scale, and for the length, I took the position where the radius is the half, or the position where the vorticity is the half of the maximum of the vorticity. Using these two parameters, we can come up with self-similar behavior for all. So I apply this scaling in terms of vorticity and in terms of the radius similarity variable. All this profile collapse together in one profile, independent of time, and also independent of Reynolds number and of tip speed ratio. So it's just once we know the maximum vorticity and the radius, we come up with one uniform profile for the vorticity.
So maybe I didn't understand here. Self-similarity. What's there's something I'm not understanding. What do you mean by self-similarity here?
So here we are looking. This is the behavior, or this is the time evolution of the vortex, the vorticity.
So for you, self-similarity is the fact that it repeats. The
self-similarity for
AC is what? What is AC? So AC. I mean, you are rho 1, 2 AC or maybe.
This one is Lambosian vortex. It's like a well-known vortex.
Yeah, that I know.
He has a shape. Yeah, he has a shape. And when we use the scaling, we got the maximum of the vorticity, and we got this scaling, and we get exactly the same profile as us. Self-similarity, in our case, self-similarity.
So the two pictures refer to what? So you have two pictures.
No, this one is the real. This one is the time evolution of the vorticity inside the vortex. This one is at t equal, let's say, 1 second. This one 4 seconds, and so on and so on. This is the time evolution of the vorticity.
Okay, at different times. At different times, right?
And this is when we apply the scaling. So I took for every profile the maximum for the vorticity scaling, okay, and I get this distance as radius scaling.
AC.
AC. For me, I defined it like that as the position where we have the vorticity is equal to half of its maximum.
Oh, that's how you define AC.
Yeah, that's what I defined my AC.
Your AC, yeah. The AC that you are using for the rescaling.
Yeah. But later on, we will see also when we took AC is like the radius of the Gaussian. So even 1/E, we come up exactly with the same profile too. Here we have minus alpha. This minus alpha coming from the definition of AC. If I remove this AC, it will be exactly minus C squared.
Here in the picture, after a while. So after a while it becomes the picture repeats itself. I mean, there's no. There's one thing I'm not understanding. What in? Can you go back? Like the
Yeah, this one.
Yeah, okay.
Yeah, it's one. Okay, this one at t equals 0, we have regeneration of this helical vortex
Okay.
for some times, but later on, that's it. It's like the video is.
Yeah, it repeats
It's
itself.
It becomes periodic.
Yeah, but this is what you are trying to see. It's really to see something self-similar here.
Yeah, I'm seeing the self-similarity inside the vortex, not the big one. I'm seeing the self-similarity inside the helical vortex. I'm moving with it and I'm characterizing the vortex.
Yeah, okay.
So that explains the second plot the fact that after two, there is one profile that is indeed like in the second plot. There is one curve that is likely different from the other.
Yeah. It can be because the vortex is not really 100% non-Gaussian vortex. We have some nonlinearities there, but we are interested in this profile, so we come up with this.
Close to zero, they coincide.
Yeah. It's close to it's close to uniform profile.
Yeah, but so at the end, these vortices they look like the Gaussian vortices. I mean, like
that's the point. We are in 3D geometry. The Gaussian is a 2D flow. The Gaussian is a 2D vortex. We are in a 3D problem, but we come up with a self-similarity with a 2D problem. That's the main part. We did the same thing, the same scaling for the azimuthal velocity, and we come up also with something close to the this velocity. But here we have some coefficients A and B. We calculate A and B for all parameter in our number and peak speed ratio. And this is the A and B for the Lambosian itself.
Did you apply regression to find this parameter?
Yeah, we did the regression. Here just uploading like let's say 4 plots. But in real, what we do, I'm making a frame moving with the vortex. We have the full life of the vortex from the creation till the diffusion. As you can see here, the velocity or the vorticity is going from maximum to 0. So there is a defect with the diffusion. So for this, we cannot see the vortex for a very long time. So there is just the life duration or lifetime for the vortex.
You can go back. How did you guess that it will behave as the Lambosian vortices? Why not another? How did you have the guess that it would be this?
So I tried many aggregation. I made this one when I put the half of the radius on the maximum. So it was trivial that I have to divide by the maximum. And I start like guessing, but later on, like we did many position. I'm selecting many position, and it's automatically. So what is the best solution or the best position that I come up with the uniform with this uniform scaling. When I plot that, so I come up with the better AC. So I define AC not like the half, but exactly like the core of the Gaussian. For example, here when I apply this scaling for the velocity, so I come up with 2 points here. So for every one, I come up with 2 vortices, so 2 positions. So for here, I have row 1, row A, and row B. But when I apply like the automatic regression, so we come up just with one row, which is the dimension of the Gaussian. Okay, and also this result, as I said, is only for one theta. The results are verified for different theta, but we have to calculate again. So A, B varies according to the parameter and also according to the theta velocity. The idea to remove this dependence on theta is why not to do the averaging inside the vortex itself. So we did the averaging in terms of velocity and vorticity inside the vortex. And we did again the same scaling, but here, as I said, I'm taking this.
Can you go back? Yeah. Okay. So here, what's again here? What are you showing here?
The first part of scaling. Okay. It was dependent on the theta. You can see here.
No, but here you are saying okay, it depends on ellipticity E. What is ellipticity E? What is E?
Ellipticity is the size of the aspect ratio between of the core of the vortex. It's not circular.
Okay.
So we have 2 normal vectors. We have in this direction, local direction.
Can you vary E? Can you? How can you vary?
So I am in the local frame. So I took this theta and I can move with the theta inside the vortex. I am in relative frame.
No, but you said something. The model is dependent on E. The model is dependent on E. It means that you can vary E. I mean, you have ways. I mean, like, is it changing the weight or something? What?
Depends on E. I mean, it depends on the direction where I am taking this.
Okay.
But also it depends because this elasticity, the size is time dependent.
Okay.
So to
So it
avoid
depends
this,
on E and theta. Okay. Okay. Okay.
so to remove maybe the dependency on the theta, we did an averaging. So now for every vortex, we have only one vorticity, one velocity.
Can you go back more
This one.
before? So here on the swirl, you have a transition growth, right?
Yeah. This is the profile of the velocity.
Yeah, but there is like a growth
It's
and
linear.
then.
Yeah. It's linear.
Okay. Do you think that it's the growth is killed by the diffusion, or if you didn't have the if you didn't have the viscosity, if you think the viscosity equal to 0?
If without viscosity, we can get something goes to infinity, but you have to do cutoff. That's what people do. So they are going to take a circular vortex, and they are putting, if they're doing U theta, they put U theta, it's like R theta. It's like a linear profile, U theta. But with the viscosity and solution stops, we get, we cannot keep the velocity goes to infinity.
Okay, it's just transition.
Yeah, it's transition. And it's not like if you took something in a cylinder and you rotate, so it will be a peak near your axis rotation, but later on it will decrease. Cannot go to infinity with this. So here when we apply this new scaling, so you see here the factor A is removed and we got exactly the Gaussian shape without this parameter A and B that we found with the first scaling. We did the same thing for the theta and we come up with the beta. And A here is the size of the ball. Here this A is the size. Another parameter we studied, it was the size. Here, this is the size of the vortex, the time evolution. This is the first round when the blade did its first round. So the vortex is under construction. So the vortex is not yet well established. So for this part is not linear. But later on, we have a asymptotic linear diffusion. And it's exactly like in the 2D. So for this, the main part or the main conclusion for this is like our 3D problem is self-similar to a 2D problem, which is the Lambda vortex. Okay, so once it's characterized, we move to the perturbation and the stability analysis of this vortex.
Also, last question. When you say vorticity, it's which component of the vorticity that becomes?
It's the axial vorticity.
The axial.
Axial, but axial in the local frame, not axial for the domain. It's in the local frame. So it's here we have the helical form like that. So it will be this is the vortex. So when we say theta, this is the vorticity inside, and this is the U theta. But it's inside the vortex and moving with the vortex, not with the big domain. This is the property of the vortex itself. So for the perturbation, so we did what we call displacement instability or displacement perturbation. So we introduce a small displacement of our blade, and we see what's going to happen. What's the reaction of the fluid, or what's the reaction of this vortex on that displacement. So for this, for example, here the dashed line is the helical vortex not perturbed, and the green one is the perturbed. So we just small displacement d, and we control this using time-dependent rotation, controlled by the frequency, 1 over t, so the period of perturbation, and the small displacement d, which is the variation, small displacement. With the two parameters, we control our perturbation, and we see what is the reaction of the helical vortex, which is almost steady with periodic rotation. It is steady. So there is no radial perturbation initially. So to calculate the growth rate, so we use relative distance between three different vortices. So we follow the three different vortices in time, and we calculate the relative distance between them. So we tried, for example, to calculate only one distance, but we found that there is one mode which is unstable, but we get the growth rate according to one distance equal to 0. So there is no correlation between choice of one distance between two vortices and the results of the stability. So for this, we chose the relative distance between three of them. So like that, we come up with a good correlation between the growth rate, how we calculate, and what we see. Okay, so for the growth rate, also here we have the time evolution of the distance, relative distance, and we calculate the growth rate according to the linear or during the linear part of the evolution. This is the growth rate that we measure. Okay, the results we found we can distinguish mainly two family of modes. There is mode with growth rate equal to 0, and they are when we have frequency integrals. We got like a modification of the shape, but it's stable. There is no transition for turbulence according to this displacement. And the other mode are the most unstable, and the growth rate is close to the 2D pairing stability. Again, we are close to the 2D, which is the pairing stability when we have two vortices or when we have stable vortices, and the vortices start to move together and to merge and to form more and more bigger vortices. This is the 2D pairing. So the most
I'm confused. Here, you said that it is stable.
Yeah.
But now you are talking about an instability. What is the instability you are talking about? Okay, can you go back?
Okay, I generate a stable vortex.
Okay, now you have a stable vortex.
Yeah, I have it's the dashed line. So I have a stable vortex and can stay there for a long time. So
and now you perturb it.
I perturb it. I'm doing a small displacement of the tip or the tip of this.
So but you expect it to stay stable, so you expect it to stay close.
We don't know. We wanted to see.
Okay. Yeah, but you hope it will, because I mean you said it is stable. So
yeah.
Okay. But then okay, go ahead. Now go forward. Because you are talking about instability, so that's what I'm not understanding. What is this instability that you are talking about?
The stable mode will change the shape, but will stay stable.
Okay.
So they have the same shape, but for a long time.
Mm-hmm.
The more unstable, this shape will become chaotic and will break down. The vortex will break down for this mode.
If it is which one?
This mode, the most unstable mode, when we have a frequency half of integral.
That's the threshold, right? 1.5.
No, the red one is the 2D pairing instability. Again, what I am doing, I have a
no, but yeah, for me, growth rate strictly bigger than 1 means unstable, right? Or it has to be really above that red line so that you see it.
No. Why growth rate has to be above 1 stable? It depends on how you are defining your perturbation. If you say you are putting something exponential minus something, so this one should be less than 1 to go down and to decay again. But in our case, I don't have any condition on the growth rate. Just when we have a growth rate, positive growth rate, it will lead to an instability or will lead to the merging of the vortex. But for small growth rate, it will take long time to get this breakdown of vortex. But for high growth rate, it will be like a breakdown very fast. Okay.
But after a long time, those modes, there will be, I mean, it's because of those modes that the vortex will disappear.
Yeah, the wake will be more turbulent. But according to the growth rate, for example, for this growth rate, it will be just after 2 or 3 rounds, it will be turbulent. For this one or something like here, it will take more than like 3 or 4 rounds to break down. For those one, no, it will be modified shape. But even if anything happens, it's not related to this displacement. to be related to other things like diffusion or the another type of instability, secondary instability or something.
How many modes used
How many modes in turn?
in this experiment?
No, for our mode, it's selected with this displacement and the frequency. So I use many frequencies, but I'm plotting here the ones that I can get really growth rate. Because, for example, for modes here and here, it's very difficult to get growth rate. Yeah. So, for example, I'm comparing here with the most unstable growth rate or most unstable mode. So you see now it's no more of the helical vortex. Here we have merging of the vortices together. And here we have breakdown of the vortex. And it's exactly the same shape here in the experiment. Even the first breakdown or the first pairing start exactly the same. Here we are using the same configuration, the same blade with same perturbation, and we got the same results as the experiment. So it was like another validation of our numerical tool that we are using.
So the numerics and the experiment, they match.
Yeah. So because I use the same blade geometry here, as I said, I'm using the blade.
No,
I'm
use
using
FSI.
the-
For this one, is you use FSI.
No. The aerodynamic is based on the geometry, it's based on the chord, it's based on the twist of the blade. So we use that geometry to generate the body forces. And we use it, has been used in the experiment. As you can see, for example, it's seen here. Here there is like, this is what we call the instability of the displacement. So here it's due to the displacement that the vortex goes close together. But if you can see here, there is like small perturbation appears on the vortex, which was not related to displacement, but they are related to the curvature, another type of instability we call elliptical instability, when we have the perturbation close to the core beyond vortex. So here we have like different instabilities at the same time, but the most important one is this pairing instability. So for example, this is one of the stable modes.
Sorry.
Yeah.
So before, when you did numerics and you didn't have the viscosity, what happened to the helical vortex when you perturb it this way?
It was other work, not mine.
Okay. What did they found on the numerics?
Yeah.
So I guess they didn't have this picture, but what did they get?
They get something close to that. Already this pairing instability was already
Observed on the
before. Yeah. But what it was not observed before, this stable modes. For them, it was always when you put displacement, it's going to be unstable.
It becomes, it's faster, you mean? The breakdown of the vortex was faster on Euler than on
the previous work, they said they cannot see this mode. For them, always they have growth rate.
Meaning you can take perturbation in your model where you have no, you're stable.
Yeah. Okay. I will show the mode for a long time.
Okay, so but on the other one, it's always
they have a growth rate. It's all that always they have a growth rate.
okay, whatever. Okay.
Also, this growth rate is also shown in experiment. When you do the same perturbation, you got this nice vortex with the undulated shape, but it's not. There is no pairing that's not. So, for example, this here I'm moving with this three vortices from where I calculated the growth rate. So you see that they are moving in space, but they are moving in phase altogether. They are moving together. So for this, there is no pairing instability for a long time. Till later on, this is like the interaction with another vortex created from the hub of the blade. But for these three vortices, they are stable according to this displacement. This is the different shape. For example, when I get frequency 1, 2, and 3, here we have this. This shape is stable, but only here we have this perturbation I was talking about. This is not due to displacement, but is due to the curvature, and this is what we call the elliptic instability. So there are the secondary stability not due to the displacement itself. And we can get this for a long time. So our vortex stay like that for a long time without any breakdown. But for the second family, here we have the relative displacement between the vortices. As you can see, they are in opposite phase. Those close and far from each other. Then here there is a pairing. I don't know why there is.
So this is numerics on what? I mean, the picture here you are showing.
Here I'm moving with the vortices.
Ah,
Yeah, here I'm taking 3 vortices like that. This is my keyboard. This is my window, and I am rotating with them to see the whole life of this vortices, from the creation till the breakdown.
but you are taking so it's a 3D, but you are just projecting on one.
It's snapshot.
It's just not.
Yeah, but the flow is 3D. I'm moving just in the snapshot to calculate the distance of the between different vortices. So this is like a little snapshot for the cylinder. I don't know why it's not seeing the same thing as there. Okay, then also in my screen is clearer than that. But anyways, here we see like this vortices go close together till they form bigger vortices and merge together to form big vortices. In the case of the stable, so always we get these vortices with the same distance from each other. Okay, here even we define the phase shift and we calculate the phase shift. Here I'm following 2 adjacent vortices and always they are in the same behavior in the cross section. So they are always in the phase. And these points where they cross the stable is related to the frequency. But in the case when we have the most unstable, as you can see, they are moving in the opposite side. And those points are exactly where the pairing instability happens. So for example, for this vortex, if I'm using 5/2, there is 5 locations where I have breakdown of the vortex. And this is an intermediate mode, not most unstable, not stable. As you can see here, there is the modification of the shape, and here we have the pairing when the pairing is stopped.
So can you go back to the previous slide?
This one?
So the number of breakdowns in the vortex correspond also to the number of the vertices.
No, these points are the points where the breakdown happen when we have the vortex cross together and breakdown. It depends on the frequency we are using.
Indeed.
Yeah, but it's always just 2 vortices, adjacent vortices. So as I said here, the another mode which is not it's unstable, but as you can see, the pairing happens far from the generation. So for this, the growth rate is smaller. The most unstable, the pairing starts from the second from this location. Okay, so this is more the most part of this is the work about the helical vortex instability. So that's what we did. So we develop numerical code, we generate the helical vortex stable one, and we perturb it, and we study the self-similarity and the stability. Now in the next part, I'm going to talk about general overview about the stability analysis and some trick or some tools how we use that in CFD. So just here I'm recalling the well-known 3D Navier-Stokes equation. If we get a stable flow and one basic flow steady state or periodic even, and we wanted to perturb it to see the linear stability. So we are linearizing around that flow. As you can see, this is the linearization, and then we don't have the nonlinear term. So the linear term is gone. And we wanted to see what is the limit of the linear stability analysis. For example, if we consider here like the plane coed flow or the quasi-coed flow, where the flow is homogeneous in 2 directions, but is only dependent in 1 direction. So UB or the basic flow is only function of 1. The equation can be modified here, where D here is the derivative according to 1. And we can even using the Fourier transformation, because we have homogeneous direction. In CFD, what we use even periodic or very like a periodic boundary condition in the Z and X. But also we have to check that this box should be like large enough to not affect the perturbation inside. So in general, the system can be written as this general form. Here we have the velocity and the vorticity. Here we have the square and we have the Orsomer-Feld operator. And even if we go for the emphasis, we are going to get the Reynolds operator. We have the coupling operator between the velocity and the vorticity, and we have the square operator relating the third direction. If we wanted to come back for the primitive variable, the velocity in the three directions, so here what's missing is the ux and uz. So we have to apply the vorticity equation and the divergence free condition to come up for the full field of the domain. So this is general form when we have like linear system, and L is the linearized operator. So here we have a linear system. It has like general solution with this form. We have the time evolution of our flow or our vector is the what we call method exponential of t over L, and L is the linear operator. And here we have the Q0 is the initial perturbation or the initial flow. Okay, in the standard stability analysis, linear stability analysis, it will be dependent on the eigenvalue of this F. But there is people that they found another way to define the stability analysis. It's not just looking for the linear operator, but let's talk about the growth of the energy. If I have energy at equal to 0, what is the maximum or what is the, we are seeing the growth or amplification of this initial energy. And they define growth G as the maximum according to all possible initial perturbation that give me the maximum of energy at a given time. So using this, we have this definition. We can come up the growth rate time evolution is the norm of the exponential Tn. Using eigenvalue decomposition, we can come up with this expression. This expression can be bounded, so we can put lower bound and upper bound for this expression. The lower bound is that the growth rate cannot decay faster than the most unstable mode. The most unstable mode is the mode with the maximum growth rate. So this is the upper bound of this growth rate. And the upper bound is just the nonlinear theorem for the norm. So we have the eigenvalue decomposition, and we have this nonlinearity where V and V minus V and V minus 1 are the single value vector. So for the
what is the meaning of V minus? V minus 1. What is V minus 1?
When we have the single eigenvalue decomposition, we can write a matrix, linear operator as V, diagonal matrix with the eigenvalue, and V minus 1 is the inverse of the matrix where we have the eigenvalues or the eigenvectors. Okay. So using this definition, if we have a normal, if L is normal, so we have P2 and V minus 1 equal to 1, and we get the upper bound and the lower bound, and upper and the lower bound equals, and we have exactly the growth rate is equal to the maximum of the eigenvalue. So this is the linear stability goes well. It's like in the Rayleigh binary stability, so it goes well because the operator is orthonormal, so all vectors are orthogonal. But what in case what we have the vectors or this norm is different, this equality is different than 1. So it will be possibility that this growth of energy be positive. So it's not always decay to 0. So there is some transient regime of this growth rate. Always the eigenvalue give us the asymptotic. So for a long time, it will be like governed by the most unstable normal vector. But in between 0 and long time, there is something happens. So there is some amplification of this growth rate.
But what if L is not diagonalizable? If the matrix is not diagonalizable,
Okay, so,
how did you do that?
Yeah, we did the composition. There is many technical decomposition that we can come up with something.
But you might have that you have a growth that is not coming from the eigenvalue.
You can always do the SVD.
Yeah. There is some techniques. It's diagonalizable, we can get the eigenvalue, but we can do the SVD, single value. Or we can do another techniques to get the most unstable modes to get this.
Yeah, okay, so you find the value of lambda that gives you a growth, but it's not necessarily an eigenvalue.
Yeah.
Okay.
According to the eigenvalue, it's always there is no growth. Because this matrix always here we are talking about the same L. The eigenvalue will be always in L. So at something like a long time, it will be governed by the most unstable. And it gives us always if it is like the real part is lower than 0, it will be stable. But in between there is something happening in between. But at the long time it will be always governed by the eigenvalue itself. So in between for the short time, so we can do like Taylor expansion near 0, here 0 plus, and we can come up with this expression always the growth rate is the maximum of this quantity that we can define as scalar product. So if there is some development, then we end up with this expression. Here, as you can see, the growth rate near 0 plus, it depends only on this matrix. And we can calculate the eigenvalue in this matrix L and the conjugate transpose of T. This value will give us the slope near 0. So if I wanted to plot my growth rate near 0, this value will give me the slope. So if it is 0, it will be always 0. If it is negative, it will be negative growth rate, but it cannot be negative because we are talking about energy. If it is positive, this slope will give us like the behavior of the growth rate near 0. So now in general, we have 3 steps. The short time is given by this value. The long time is given by the maximum eigenvalue, and there is like an intermediate growth rate. We can calculate this growth rate, this norm of the matrices using numerical algorithm. For example, this is an example for the positive flow 2D for a non-symmetric 1000. At long time is always stable. But in between, there is a growth rate. So in the intermediate process, there is amplification of energy. This can be seed for the turbulence. Why? Because this comes from only from linear term, linear part. But at a certain point, this point can, with nonlinear effect, can go for the turbulence behavior. And another thing which is important for us, for example, as I said, the way we define this growth rate is the maximum of the energy over all possible initial perturbation. We have this analytical expression for the growth rate, but we don't know which initial perturbation gives us this maximum growth rate. So to do that, we have this expression, which is the equation we are solving. I'm looking for the initial perturbation Q0 that give me the maximum growth rate at T start. So I'm supposing that Q0 is equal to 1, and I can normalize this Q, and I come up with this expression. Here we can see here is the propagator, is the linear operator of the initial condition, and is equal to the amplification of that initial condition. And this is the typical single value decomposition. So here we have a matrix of single value decomposition. It will be U, and this is the diagonal the eigenvalue. Single value, and this is the transpose conjugate of it. Now, if I have G over T, if I have this growth rate, can I come back for this Q0? So this it can be done using the SVD. So this SVD, here we have this operator. In our operator, this is the exponential matrix. We have it. Q0, it will be corresponding to the first column. And the amplification or Q star, it will be corresponding to the first column on the right side. So no one just the matrix L or LT star. We did the SVD for this matrix, and we can come up with the answer and the initial condition of the perturbation. So we need that. For example, okay, we said doing this linear analysis, we get this maximum growth rate. So from that maximum growth rate, I can go back for the initial condition that may be this maximum. And I can put it in the nonlinear system to get this turbulence. Okay, in general, when we look for the nonlinear system, when we have everything without any nonlinearization,
3 minutes.
So just when we talk about nonlinear system, we are like perform a disability analysis of the Navier-Stokes equations for any perturbation. It comes out like equivalent problem as like optimization. So what is the initial condition or what is the initial perturbation that give me a target energy at a target time? So, and we can develop Lagrange for that expression using the different condition and different initial, different constraints. So, for example, here we have this is our cost function. Here we have we need that the initial energy should be equal to the target energy E0. Here we have our continuity equation, and here we have our divergence free or our. This is the momentum equation. This is the continuity equation. This lambda u plus and v plus are the multiplier of Lagrange. And so as optimization problem, to get the maximum of L, so we have to derive L over all the variable and make them equal to 0 one by one to get the system. So by the end, we come up with this the adjoint Navier-Stokes equations, which depend U plus is the adjoint variable or the dual variable. It will be depend on the basic flow and also depend on the perturbation I'm putting. So to solve this problem, it will be iterative scheme. So the first step, I'm solving the Navier-Stokes equation from first guess. I start with this initial profile and I go from 0 to the target time. By using this target time, I can update the dual variable, which is u plus. This is coming from the condition that we have one of the equation of Lagrange, the derivative of Lagrange equal to 0, give us this equation. So now the dual at t equal target time, it will be the initial condition from this equation, and I go back to t equal to 0, backward. And in the backward, we will have to move this equation. We have to increase the Lagrange operator. Just one thing here in this equation, as you can see here, the dual part, we have the u. So I'm gonna in the one direction, I have to save all u in time because later on I need them in the backward direction. So anyways, it will be iterative process till we converge where the optimum initial perturbation that gives me that target energy at that target time. So here an example of people what they did. So for example, here it's in paper. So here this is the growth rate for different for the same target energy, but for different target time. And this is the growth rate for different initial
Sorry for the nonlinear problem.
This is fully nonlinear.
Yeah. So how you find the right perturbation to get the maximum growth?
The maximum growth at the target time.
Particular time.
Yeah. Because after that particular time, it can be another initial condition that gives me maximum. And here the temporal evolution of their initial condition, I think, for one of these conditions. Also, this method have been used to get something like what we call threshold of energy. What is the initial energy compared to the Reynolds number? When we are varying Reynolds number, how this initial energy varies according to the Reynolds number. And this is the coefficient that they got Reynolds number power minus that, or it should be minus one. Reynolds number minus that. Okay, so this is just a numerical change. As I said, for the base flow, sometimes we need to create the base flow. It's not always easy to create base flow for a particular case. So there is some techniques that we did initial guess, and we filter, we kill all small perturbation, we run again, and we iterate many times till we get very smooth base flow, steady one. As I said, for the dual Navier-Stokes, we need to save the velocity of the direct problem every time. It will be very costly, so people using what we call checkpointing. So they save in some period, not all the time, they save in some point. And when they come up with that point, they solve again Navier-Stokes equation for a short period. This is your question. You said, what if not diagonal? So there is many algorithms that can be used to get to reduce the size and to get this diagonal. And also this is SVD, and people now they are using dynamical decomposition to get the mode the most unstable as well. And, thank you very much.
Question? No. And ask whether we can do the experiment.
Yeah, maybe.
We asked all the questions during the talk.
Russian.
Okay, any questions? No?
Russian similar.
Okay, thank you again.